Hi, everybody. So this topic is parity checkers and parity generators. And the idea of parity is used in serial data transmission. So if we had a set of data that we wanted to transmit, so I'm writing my digital word here from least significant bit on this side, most significant bit there, and I could have some set of data in here that I want to transmit, right? Now the idea of parity, and you may have noticed parity as a setting on your computer for some serial transmissions. The idea of parity is to send along a parity bit. Now, what that bit is depends on what data you're sending and on whether you've chosen even or odd parity. So if you've chosen odd parity, that means total number of ones, including the parity bit, should be odd. Okay, so for odd parity, the total number of ones, including the parity bit, should be odd. And for even, total number of ones, including the parity bit, should be even. Okay, so for the number that, or the word that I just put up there, the 1010, if I wanted to transmit that and I was using odd parity, I would make the parity bit 1, so that the total number of 1 bits, so this one, and this one is 3, which is an odd number. Okay, if I was using even parity, I would make the parity bit 0, because then I would have just 1, 2 ones, which is even. Okay, so the parity bit, what you pick for the parity bit depends on what the actual word you're sending is and whether you've chosen odd or even parity to be your setting, right? So this is used to know when, for the person receiving, did that message come through correctly? Okay, so if one of the bits is wrong, then the parity count is not going to match up anymore, and they're going to know. So in order to implement this kind of scheme, you need 2 things. You need a parity generator on the sending end, and you need a parity checker on the receiving end. So first, let's just look at parity generators. Okay, so we'll look at generators, and first let's look at even. So the even parity generator is making use of the XOR gate's ability to check if bits are the same or not. So I'm going to send all the bits of my word, my data word, I'm going to send that through the checker, or sorry, through the generator, and it's going to generate as an output the parity bit. Okay, so for the example above here, it was 1010. So I'm sending in 1010, and it's going to generate the parity bit. So if I follow this through, the XOR gate, if the 2 inputs are different, it's going to be high, and then it would be high here. Now those 2 highs are going to combine to make a low. And that works because for even parity, I already have 2 ones equal to high. So my number of ones high is already even, so the parity bit should be 0. So that's correct. If I were to send a different piece of data through, suppose I sent, I'm putting this in green now, suppose I sent 1011. Well, now this will still be 1, but this will change to 0, and this will change to 1, which means for the green data, I'm sending 1010 or 1011, and the parity bit here is actually 1. And then when I add up and I do the count, I've got 1, 2, 3, 4 ones, which is even. So the parity bit has been set correctly. Okay. The only difference you need to make to change this parity bit generator into an odd parity bit generator, the only difference you need to make there, just finding a different pen color, if I want to make this odd, the only thing I do is I add an inversion bubble on the output, so that last gate is an XNOR gate instead of an XOR gate, and then it will generate the right parity. So for the same example in green, if I was sending 1011, the parity bit calculated by the circuit above would actually be 0, which makes sense because I already have 1, 2, 3 ones, which is already odd. So my parity bit should be 0, making the total number of bits, including the parity bit, still odd. Okay, so that's how parity generators work. Now, the next thing we have to look at is the parity checker, right? So on the receiving end, how do I know if my my information has been transmitted correctly? So the parity checker, and this is for even, is going to look like this. So interestingly enough, for the first bit, it looks exactly like the generator, but then we add in a further XOR because we're sending it now the parity bit. So we're giving it the data 2, 3, 2, 2, 2, 1, 2, 0. So we're giving it the most significant bit to the least significant bit, but also as an input, it's getting the parity bit as an input. And the output is this indication, so this indicator, and it's going to give us a 1 if there's an error, or a 0 if there's no error. So if the parity bit and the data add up, it's going to give us 0, meaning no error. If they don't, it's going to give us a 1 for an error. So as an example, let's take the original data we had, which was 0, 1, or sorry, 1, 0, 1, 0. And if we go back, the parity bit that we generated for that for the even case was should be 0, right? Because we already have an even number of bits. So this was 0. Now when we send this through, let's follow it through. That's a 1, that's a 1. Those two together make a 0. That's a 0. So this is 0, meaning there's no error. And our parity bit was set correctly, our word has been transmitted correctly. So essentially what it's saying is that the data has been transmitted correctly. If one of these bits were to come through wrong, you would get a 1, which would indicate an error. Unfortunately, if more than one bit comes through wrong, it won't be able to detect that. So it's a pretty primitive level of data checking, but it can check if a bit comes through wrong. Now, to convert this circuit again to an odd checker, it's quite easy actually. So if I want to convert it to odd, I'm going to add an inversion bubble here so that that output gets inverted, and that would change it to an odd parity checker.